All right, good morning. I'm Nick Courtwright. My paper was on epoxies. So this image here is actually looking through a scanning electron microscope, and another machine is looking at the different layer thicknesses, and you can see the number of voids in the material. So my paper was the influence of layer thickness on mechanical properties in stereolithography. It's from the Rapid Prototyping Journal, published in 2006. And the specific scope of the study was to study the effects of layer thicknesses of the SL components. During stereolithography, about 95 to 98% of the liquid resin solidifies. The other few percent actually causes lower strength and lower toughness in the parts. And that's why the SL parts go through a post-curing process. So the post-curing process is exposing the part to UV light, which improves the strength and toughness of the part. However, it can introduce shrinkage and residual stresses. And so this paper wanted to point out that by choosing the right parameters for the SL process, you can minimize the negative effects of the post-curing process. So their key question addressed is, what is the effect of layer thickness on yield strength, ultimate tensile strength, impact strength, and induced residual stress? So this is a blown up picture of the scanning electron microscope looking at the parts. This is actually at 125 micron level of the epoxy resin, and this voids show up in different layer thicknesses, and they kind of use this to back up their results in the experiment. So the material used for the experiment was an epoxy resin, Ciba-Tool SL5530. They looked at the process conditions of yield strength, ultimate tensile strength, impact strength, and residual stress and strain relief rate. And they used a universal testing machine for the yield strength and impact strength, or for the yield strength and ultimate tensile strength. The Atre impact tester was used to measure the impact strength, and the hole drill method was used to determine the residual stresses in the parts. So these are the specimens they used for the testing, and people always ask about size. The top one is about 6 inches long, and the bottom one's about 5 inches. So the first key result from the study is, how does layer thickness affect yield, ultimate tensile, and impact strength? So for the studies, they created 10 specimens in one setting and tested each specimen and took the average of it to minimize the error. And this is the study for the yield strength, ultimate tensile strength, and impact strength. And in each case, they each decrease with the increased layer thickness. So they used the three most widely used layer thicknesses in stereolithography, which is 100 micrometers, 125 micrometers, and 150 micrometers. And in each case, the yield strength, ultimate tensile, and impact decrease with the increased layer thickness. Second key result was, how does the layer thickness affect residual stress and the strain relief rate? This case also used the 10 specimens and took the average of it. And in this case, the residual stress was lowest and the strain relief rate was highest at a layer thickness of 125 micrometers. And they said anything above that would decrease both the residual stress and the strain relief rate. So for a summary, the strength of the SL part increases with a smaller layer thickness. The microstructure analysis shows that the number and size of voids increases with layer thickness, and the low residual stresses and high strain relief rate occur at a layer thickness of 125 micrometers. As far as a personal critique of this research, although it's a very well written paper and the experiment seems easy enough to follow, and it really helps the designer to understand what correct parameters to choose to have the best results out of the process.